Hello everyone, today we will do a new method for computing the integral e equals the integral of 1x squared plus 1, don't forget the dx. We know that this equals the inverse tangent of x. We proved that using a trigonometric substitution, but this time we will use complex numbers. How? We know that this denominator is irreducible in the real world. But in the complex world, things are different. If we call the polynomial p for x equals x squared plus 1, and let it be 0, we have two solutions. X equals I or x equals minus I. Okay, so we can write this polynomial like this. X x minus I, x plus I. So our integral will be the integral of dx over x minus I, x plus I. Okay? Now we have to split the fractions. We have I equals the integral of a coefficient I dx over x minus I plus the integral of b dx over x plus I. There is a famous method how to calculate these coefficients when you have an equation of degree 0 over two equations of first degree. First, what we will do is put this to equal 0 so that x equals I, okay, and hide it. Put the dx here, the I here, and the I in all the x's. So you get 1 over 2i, okay? So a equals 1 over 2i, which is the same as if we multiply the denominator and numerator by minus I, we get minus I over 2, okay? Same with b. Put this equals 0, so x equals minus I, put minus I here, so you get 1 over minus 2i, so 1 over minus 2i. Multiply the denominator and numerator by minus I, you get I over 2. Alright, let's continue. We have e equals the integral of minus I over 2 over x minus I, and don't forget the dx, plus the integral of x plus I in the denominator, and the b is I over 2, so we write I over 2. This is just a constant, so we can move it outside the integral. We get minus I over 2, the integral of 1, we write it dx over x minus I, plus I over 2, integral of dx over x plus I. This part will be minus I over 2, natural log of x minus I, plus I over 2, natural log of x plus I, plus a c. Let me write it c prime, okay? Just to do some simplification, you will see why. Alright, but this is imaginary. We have a real integral. How to get something close to inverse tangent? We can use the polar form, which is a way to deal with angles. See, there is a relation between inverse tangent and angles, and the polar form has that relation. So we can put the inside to be something. The inside to be something. Yeah, there's a polar form. Okay. Let z let z1 equals this part, which is x. Wait, sorry. Yeah, x minus I, okay? This part will equal to, first the radius. The radius is square root of this squared, x squared, plus minus 1x squared is just 1, so we get 1. Then put the e to the power of I and the angle. The angle is the same as inverse tangent of y over x, which is minus 1 over x. Alright, same with this z2. Let it be x plus ai equals square root of x squared plus 1, because 1 to the power of 2 is just 1, okay? So e to the power of I inverse tangent of 1 over x. Or let's continue. I will equal to minus I over 2 minus I. Put the z1 here, you get ln. By the way, when you have ln of a product, it equals to ln at the first term plus ln in the second term. So we get ln square root of x squared plus 1 minus I over 2 ln e to the power of I inverse tangent of minus 1 over x. Okay? And in fact, inverse tangent is an odd function. So we can put the minus here. Like in the sinus. It's just the same thing. Okay? So don't forget the other term, which is plus I over 2 ln x squared plus 1 plus I over 2 ln e to the power of minus I inverse tangent of 1 over x. Wait, there is no minus. Okay. This part is cancelled with this, leaving us with x equals this part plus this part. Wait, forget something. This ln is cancelled with the e. I multiplied by I is minus I, and the minus is minus plus, so together minus inverse tangent of 1 over x plus I with I is minus. Wait, I forgot the 1/2, minus 1/2. Okay, so here I with I is also minus, so minus 1/2 inverse tangent of 1 over x. Yeah, don't forget the plus c prime plus c prime. Okay, so I equals, this part is just the same, so we say minus inverse tangent of 1 over x plus c prime. Okay, but this is not inverse tangent of x. We can do some tricks to come with that expression. We know that. Oh, wait a minute. Yeah. We know that inverse tangent is another, it's also another function. So we can put the minus here again, just to simplify things a bit. Or leave it like this, okay? Sorry for the confusion. Anyways, this is better. Okay? We have inverse tangent of 1 over x equals something, okay? I wanna simplify it a bit, because it's just weird to have something like this. 1 over x inside the inverse tangent. So we have 1 over x equals tangent of L, so that x equals tangent L 1 over tangent L, okay? Yeah, which is the same as cotangent L. So x equals, so L equals inverse cotangent of x, okay? Put it here, you get E equals inverse cotangent, wait a minute, inverse cotangent of x. Okay, we will continue with simplifying this part and make it inverse tangent, okay? If we took a unit circle, for example this unit circle, and put theta to be this, okay? This part, yeah, here, right angle. This part from this to this is tangent theta. When you do a theta prime, it equals also to cotangent theta prime, okay? You know this theta prime plus theta will equal to pi over 2. So theta plus theta prime equals pi over 2, okay? And this theta is the same, if we put this is equal x, so theta is the same as inverse tangent of x plus, and cotangent is the same as inverse cotangent of x, okay? This will equal to pi over 2. This is very nice. We can put this here, so we get, wait, minus cotangent, minus inverse of cotangent of x will equal to inverse tangent of x minus pi over 2. Yeah. Put this here, so you get E equals what? Equals tangent. Yeah, wait. Tangent, inverse tangent of x minus pi over 2 plus c prime. You know, this part is just a constant. We can replace it with a c, another constant c. Okay, so we get E equals inverse tangent of x plus c. That's the answer. Okay, I hope you like the video. Imagine numbers are the best. They are very fun. Okay, goodbye. The next video we'll do, by the way, next video, we'll do an integral for 1 over x cubed plus 1 dx. This integral we'll use the usual way, which is factoring the denominator and flip the fractions, etc. But you can actually use the, complex numbers in the part where you have something squared plus 1, which is the same as this part, okay? So I will not use it again because it's the same thing, okay? But what I'm gonna do is something else in the next video, which is when we have 1 over x squared plus constant squared.